Okay, folks, this is Professor Kunchberry again. I know we had a little bit of a technical difficulty on Sunday, and as I promised, I'm recording this tape here, this session, so that you can go back and review some of the material we talked about on Sunday. So the first thing we need to talk about here is encryption, right? We started talking about the security axiom, the CIA, the confidentiality, integrity, and authenticity of we call it the the security axiom. The security axiom has three components, and those are the three components: confidentiality, integrity, and availability or authenticity. Now, how do we achieve each of them? I think we briefly mentioned this. We talk about being able to achieve confidentiality through encryption, right? I mean, you use encryption to be able to achieve confidentiality. So what you're doing during encryption, you're taking what we would call plain text, you apply an algorithm and a key, and the resulting component is called a ciphered text or encrypted text. The meaning is still there, but only the sender and the recipient can, or maybe hackers sometimes would be able to tell the meaning of the encrypted material. You have to decipher it, and then you'll be able to tell the content of that message. Now, remember we talked a little bit about being able to encrypt. Remember, when you talk about encryption, what you are doing here, you're taking plain text, and what you're doing with this plain text, you are actually applying an encryption algorithm, right? You're applying, I went too far here, you're applying an encryption algorithm, and you're going to get the ciphered text, right? And the ciphered text has the same meaning as the plain text. You did not change anything. You just converted it into a completely different format that anybody at random will not be people at random or machine at random, entities at random will not be able to tell the meaning of that message. And to decrypt, you're going to reverse the process. Now, this works only for symmetrical encryption, but for asymmetrical, things get a little bit different. So the mathematical equation is fairly simple. It's actually, we're going to take a message M that you see right here. We're going to apply a key to it right here, right? What we're going to get a ciphered text. The C here represents the encrypted message, okay? The mathematical equation here. So we're going to encrypt, excuse me, we're going to encrypt a message M with a key K, right? That's going to be equal to C, the ciphered text. And to decrypt, we're going to take the message, the ciphered message, which is that C here. We're going to apply the same key to it, and we're going to get M. I don't have this here. That's an omission on my part, that DC of K is equal to M, right? So what does that mean? What it is saying, we take a message M, we apply a key to it, and some algorithm, we get an encrypted message. And to decipher, we need to use the same key. And we're going to apply the decipher algorithm with the encrypted message, and we're going to get the original message. And this is called symmetrical algorithm. Notice what's very important here is the K. The K here, they are the same keys. one of the weakness of symmetrical algorithm is the need to be able to send that key to the recipient safely, and that's not always easy to do. As we continue with this course, you're going to see different ways of sending that key to the recipient. It's not always easy. Now, for asymmetrical algorithm, it's a little bit different, right? So here, we're going to take an algorithm, we're going to apply it to the message using a key, right, K1, we're going to get C. That's the encrypted message. To decrypt, we're going to take an algorithm. It may not necessarily be the same algorithm. We're going to apply it to that encrypted message. But this time, the K here is different. Okay? K1 here is not equal to K2. What it means in real life is that the key that you use to encrypt is not the same as the key that you use to decrypt. That's going to play a very important role with what we're going to do later on using asymmetrical encryption. So remember, to recap here, symmetrical encryption, you use the same key to encrypt and to decrypt. For asymmetrical, you're going to use a different key to encrypt, which a lot of times we call a public key, and we're going to use a private key to decrypt. Okay? So I hope that makes sense, right? So think about this a little bit. It's the mathematics behind this can get very complex. Now, let's go back to our encryption here, our little diagram that shows encryption. When you apply this key here, this is the secret, right? The key is the secret. So if somebody gets hold of this key, we're in trouble, right? Which means they can hack into, and remember what we said, this message is intended for a recipient. Now, if anybody in between the sender and the recipient find out what this K is, they will be able to decrypt that message and be able to know the meaning of that message. Here, it's a little bit different. That K1 here can be public, right? The K1 can be public. Everybody can tell what K1 is because it is only used to encrypt. Okay? It is only used to encrypt. It is not used to decrypt. Okay? Remember, let's suppose I want to send you this message. All I need to do is, okay, I know John, for example, and I want to send John an email, an encrypted email. So I go and find out, well, what is John's, public key? So I find out what John's public key is, and John may have it. He may send it to me. I would use that public key to encrypt that message. I'm going to send that message on a public network or some type of network, and it gets to John. Nobody in between me and John will be able to read that message because they don't have the private key. Only the recipient of that message has the private key and will be able to decrypt that message and look at the content. Okay? Now, later on during the course, we're going to talk about the relationship between K1 and K2 and how do you get K1 and K2, and that's going to to be a little bit more complex, we're not going to look at the algorithm on how to generate K1 and K2, but K1 and K2, just to summarize, has to do with large, very large prime numbers. This algorithm was used for the first time during the Second World War by the British. The British were the first folks or engineers or cryptographers who were able to develop this methodology or this algorithm. It's only with the introduction of computers in our daily life now that we hear about asymmetrical algorithm. Okay? Now remember, we talked about a little bit something else we talked about in the session on Sunday was the concept of integrity. Remember, integrity has to do with the fact that the information does not change between point A and point B. In other words, if I send you an email and I tell you to sell 100 shares of my stocks, somebody does not intercept that message and change it to 200 shares of my stocks. Right? If somebody was able to do that, then that could they could have some really bad consequences, because John is sending something and Sherry is receiving it, and Sherry doesn't know if she's receiving what John sent. There is no concept of being able to compare these two messages and being able to tell if that message has not changed during its transmission between John and Sherry. Okay? And that's important. And as somebody said in class last time, this whole process is called hashing. And we'll talk about, today we use what we call SHA 128 or SHA 256, and we're going to talk about this a little bit later. Now, the next part of the slide here is talk a little bit about different type of ciphers. We talked about Caesar cipher, character substitution, transposition, and character shift. And these are called primitive cipher because they are not applicable today with computers. You can go through those very quickly and create what we call brute force attack, which we're going to talk some more later. Slightly better is Wiener cipher, which is a little bit different, and I'm going to show you how to do that tomorrow. I'm going to send you a tape and you're going to see how we can create Wiener's encryption. Okay, this is the table that we're going to come back to and talk about Wiener's table. So notice that the top is A, B, C, D all the way to Z, and the second row starts with a B, right? The A went all the way to the end there, right? Let me go back. Okay, so here, the next, you're going to start with a C, right? Because you're switching one over, right? The next time you're going to start with a D, the next time you're going to start with an E, the next time you're going to start with an F, right? Remember, at the end, if you're starting with an F, what happened to A, B, C, D, E? Well, they went to the end of the alphabets, right? Now you get F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, X, W, X, Y, Z, and then at the end you tag what you miss in front, so you're tagging A, B, C, D, E. That's how you create the Wiener's table. Very simple table. Notice that you have A, B, C, D here, you have A, B, C, D here. Very important, right? All the way to Z and all the way to Z. Now, how do you encrypt using this process? Okay, I'm not going to continue because we are almost getting close to our 15 minutes. Otherwise, the YouTube may not let us upload this, so I'm going to end it here.